What if I told you that infinity is not just a concept, but a hidden architecture that shapes everything around us? Today we'll explore how infinity manifests in our world, from ancient Greek paradoxes to the most beautiful fractal ever discovered. First, Zeno's paradox, an ancient puzzle that seemed to prove motion itself was impossible. Then infinite series, how adding infinitely many numbers can give us a finite answer. Next, fractals, shapes with infinite detail hiding within finite boundaries. Finally, the Mandelbrot set, infinite complexity born from the simplest equation imaginable. Let's begin our journey into the architecture of infinity, starting with a race that has puzzled humanity for over 2,500 years. Zeno of Elea, a Greek philosopher, posed paradoxes that have haunted mathematicians for over 2,000 years. Imagine a race between Achilles, the fastest runner in Greece, and a tortoise. The tortoise gets a head start. Achilles runs to where the tortoise was, but during that time, the tortoise has moved ahead. Achilles runs to that new position, but the tortoise has moved again. No matter how many times Achilles reaches where the tortoise was, the tortoise will always be slightly ahead. According to this logic, Achilles can never catch the tortoise. Zeno had another puzzle. To walk across a room, you must first walk half the distance, but before you can walk half, you must walk half of that, which is 1/4, and before that, 1/8, and before that, 1/16. There are infinitely many steps you must complete before you can even begin to move. How can you take infinitely many steps in finite time? Both paradoxes share the same core question. How can infinitely many things add up to something finite? The ancient Greeks had no answer, but modern mathematics does. The key lies in understanding infinite series. An infinite series is a sum with infinitely many terms. It sounds impossible that adding infinitely many numbers could give us a finite answer. Let's visualize this with a simple example. Start with a square of area 1. First, we shade half of it. That's 1/2. Now shade half of what remains. That's 1/4 more. Keep going. 1/8, 1/16, 1/32. Each time we shade half of what remains. As we continue forever, the shaded area approaches exactly 1. 1/2 plus 1/4 plus 1/8, and so on, equals exactly 1. Mathematicians express this with a beautiful formula. The sum of this infinite geometric series is 1 divided by 1 minus the common ratio. When the ratio is 1/2, we get 1 divided by 1/2, which equals 2. But wait, that's not what we saw. That's because each term starts from 1/2, not 1. So the sum is indeed 1. Now we can finally solve Zeno's paradox. Achilles must cover infinitely many distances, but watch what happens when we add them. If Achilles runs at 10 meters per second and the tortoise at 1 meter per second, with a 10-meter head start, the total distance Achilles runs to catch up forms a geometric series. This infinite sum equals exactly 11.1 meters. And the time? Just 1.1 seconds. Infinity resolves into the finite. But not all infinite series behave this nicely. Some series converge to a finite value, while others diverge to infinity. For example, 1 plus 1/2 plus 1/3 plus 1/4, going on forever, actually grows without bound. It diverges. Infinite series reveal that infinity can be tamed, measured, and understood. But what if we could see infinity not just in numbers, but in shapes? Let's explore fractals. Fractals are shapes that contain infinite detail within finite boundaries. Zoom in and you'll find the same pattern repeating forever. This property is called self-similarity. Each part of a fractal looks like a smaller copy of the whole. The Sierpinski triangle is perhaps the simplest fractal. Start with a solid triangle. Remove the middle triangle. You're left with 3 smaller triangles. Repeat this process for each remaining triangle, and again, forever. The final shape has 0 area, yet it still exists as a geometric object. Infinitely many holes creating an infinitely detailed boundary. The Koch snowflake takes infinity in a different direction. Start with an equilateral triangle. On each side, add a smaller triangle in the middle. This creates more edges. Repeat forever. Each iteration adds more bumps, making the perimeter longer and more complex. Here's the paradox. The area remains finite, bounded by the original triangle, but the perimeter grows without limit, infinite length surrounding finite area. Fractals show us that infinity can be woven into geometry itself, but there's one fractal that surpasses all others in complexity, the Mandelbrot set. The Mandelbrot set is perhaps the most famous mathematical object ever discovered. It emerges from the simplest possible equation. Take a number c on the complex plane, start with z equals 0, then repeat, z out becomes z squared plus c. If this process stays bounded, the point c is in the Mandelbrot set. If it escapes to infinity, it's not. Let's watch this definition come to life. For each point on the complex plane, we apply the iteration. The black region is the Mandelbrot set, points that remain bounded forever. The colors around it show how quickly other points escape to infinity. But here's what's truly remarkable. Zoom in on any part of the boundary, and you'll find infinite detail. Smaller copies of the whole set appear everywhere. Spirals, seahorses, lightning bolts, all generated by that one simple equation. The Mandelbrot set contains infinite complexity within a finite space. It's a window into how simplicity can generate endless intricacy. From one equation, a universe of structure. And that is the architecture of infinity. From Zeno's paradoxes to the Mandelbrot set, we've seen how the infinite weaves itself into mathematics and reality.